Welcome everyone to last talk of the day on this one, C++11 optimization and performance. I usually start off with this question, why? Why this talk? I like to say, well, what made me think that I was going to talk about this stuff? Well, I go around doing quite a bit of C++ training, consulting, and talking to other people, and people use C++ because they want control, they want optimization, they want performance, they want to get everything out of their machine. And I've seen a lot of people talking about things saying, should I do this, should I do that? Which is more efficient? So what do they mean by efficiency? What do they mean by optimization? Those are some interesting questions all the time. But I've seen a lot of advice in the Times, and they're going, well, it also appears to be a little bit of sort of kind of, well, a bit of this and a bit of that. So you'll get something, so people are asking, should I do pre-increment or post-increment? And I'm thinking, well, actually, most of the time, that's going to make absolutely no difference whatsoever on integers. If it's your own iterator type, possibly, but apart from that, it really isn't going to make a great deal of difference. Oh, yeah, well, when I was in college, I was told I should be using shifts rather than divides. And I'm going, well, yeah, a compiler usually does that for you, if it's a constant anyway. And, well, yeah, divides are a bit more expensive than these ones. They're probably quite an expensive one altogether. But really, is that the limit of the advice that we're given? Surely there's got to be a better way. Surely there has to be some way of doing this in a more structured way. And then you'll get some people who might say things like, avoid array writes. This is one that Andrei Alexandrescu says, well, yes, array writes do have a problem because you have to do a read and a write, and then you haven't got, and you can't put them into registers. Yes, that's fine. If you're finding that's a problem, then probably there's something else that you're dealing with. What's the bigger picture here? Oh, well, move semantics, they're going to be great. Big thing on C++11. Yes, they're a performance advantage. When? Why? How do they fit into this picture? Oh, we should be doing cache-friendly programming, data-oriented programming. You get Mike Aston, or his name is David Aston, I've forgotten his name, doing games programming and data-oriented programming and pulling his hair out, telling us we've all done it wrong. Well, he's probably right, but for a games programmer, when you've got 16 millisecond batches, essentially there's a very different thing than if you're doing data lookup, you're doing a web service, or you're doing some bulk calculations. It's very different. Ah, well, multiple threads will save us all for this one. Well, the answer to that one is definitely no. It will probably create more problems than it will solve. So I've been trying to teach people about this one or get them to think about this, and I went, well, there's more of a kind of a story. And there's a story that sort of kind of goes like this, and this is what I try to get people to think about. So you start off and it says, well, your application is too slow. Well, yes, fine. If it's not too slow, then that's the end of this one here, and we'll just all go to the bar right now. So you start profiling, you start timing it, you go, well, what's going on? And what I usually find is that the first thing at that next level is you're doing something silly. You're going like, oh dear, it's the full face palm at this point, where you start thinking, why are we calling the database every time in the loop? Why are we doing this one? Why are we doing that? Why are we doing that? And so you find that there's usually some silly little thing that you've done that's consuming a lot of time. It may actually be a surprise to you that the thing that you're looking at takes a lot of time. But you can sort of kind of get quite a long way with that first part of there. And that's not really about sort of C++ optimization or whatever, that's just good programming. Right, okay, so we get that one out of the way. Then the next step is, right, okay, what are we going to end up? And then usually what I found is that then your profiling is going to tell you that malloc or memcomp or memcopy at the top, that you're spending a lot of time doing memory management. And this is really quite common. And I've seen a number of people get to this one and go, oh, you're at that stage of optimization, are you? This is a process I've seen happen in a number of places. So it's not about, do I just do this or that? The answer is, no, there's a story going on here. We can get to something faster. Why? What do we do about that one? Okay, well, actually, at that point, we then need to start dealing with things like temporaries. We need to start thinking about our memory allocation, pre-allocating memory rather than bits and pieces. Maybe you want to choose, we're using vector, we're not using reserve, those sort of kind of things like that. Maybe we should be using move. Maybe we should be using in place rather than just creating stuff. How do we avoid the overhead of dynamic memory allocation? We'll come back to some of those ones. Right, so you somehow get rid of that one, and then you go, oh, okay, we've stopped throwing cycles away. We've stopped generating all these cache misses and other things with thousands of cycles going on malloc. And then you go, right, okay, now at this point, we can start looking at, oh, our algorithm, is it order n squared, in order log n, order 1? What does that mean? And then we can start getting those benefits because we've stopped throwing away stuff. So stop doing silly things, stop throwing away time on malloc and copying, and then you get down to that one. This then really you start asking about operational profile and data access patterns. Have you got a read-heavy or a write-heavy application? It makes a big difference as to whether caching makes a difference to you, caching both at the application level and at the hardware level. And then right down at the bottom, you're starting to deal with, then you're really getting down to it, which is like memory bandwidth. And you're then starting to say, well, actually, how do I lay this one out? How do I use the cache in a better way? But to start playing around with sort of trying to do cache-friendly stuff when you're throwing things away on malloc is you're starting at the wrong point. So my view is that you should be thinking of this in a more structured engineering approach, top-down, measuring it that way. We're going to go through some of these things. I'm going to show you bits and pieces about this one, but if there's one thing you take away from this one, it's that. And you'll see that again at the end. It's not a set of tweaks. It's an engineering process. And we're going to have a look at a few things here. It's a multi-level problem. It's everything from architecture and design. One of the things I would like to stress is domain knowledge. Domain knowledge is really useful. You can't expect the compiler to do stuff that you can't communicate to it. And there's a lot of things that we need to understand about what you're doing, how you use it, as to whether something is faster or not. Your access patterns. The STL is great. I like the STL. The STL is good, but we better use it in the right way. There are alternatives to it. It's not always the right thing, but if well used, in a lot of cases, it is. Strings. So Phil Nash has just been talking about string handling. I'm going to mention string handling, so I will have a few things to say on that area about alternatives. Memory allocation we mentioned, move semantics, and modern machines. Modern machines are quite different, and they're surprisingly different, and compilers also surprising as to what they can and can't do. Profiling tools, very useful. They tell you where the problem is. They don't tell you how to solve the problem. If you see memcopy at the top, which I saw recently on one, well, you could try optimizing that memcopy. And I'm going, well, if you notice that says memcopy SSE41, it's a compiler intrinsic. The answer is you're unlikely to improve that one. Stop calling memcopy. Why are you calling memcopy? And it's getting you to think about that one. It's not just what's there, but how do I get rid of it? How do I reduce the number of things I'm doing there? So it's actually an engineering process rather than a series of tweaks. No doubt you're familiar with the Donald Knuth paper from 1974 that everybody quotes, and it says, blah, 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 premature optimization, blah, 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 we should forget about it 97% of the time. There's another section later on that I want to refer you to, which is this one. So that's 1974. That's quite a long time ago. It's 43 years. And he's then saying even a few years before that. So we're into 45 years plus. A few years ago, Steven looked at these Fortran programs, blah, blah, blah. The bit that's important here is how do you produce something that's as good as the hand-optimized ones? We found ourselves running into the same problem. The compiler needs to be in the dialogue with the programmer. It needs to know properties of the data and whether certain cases can arise, etc. We couldn't think of a good language in which to have such a dialogue. So back in 1974, he recognized that the domain knowledge, knowing properties of the data and how you use it, is absolutely key to this one. And you can't put it into the compiled code in a way that the compiler can do this for you. It's your job. So domain knowledge, very important. Modern CPUs are fantastic and amazing pieces of kit. They've got 5 billion transistors in them and counting. Tiny little things of 14 nanometers, and I'm just amazed at what they can do. They have long pipelines, 10 stages or so, because they're splitting things up into lots of sections, because each one then can go as fast as possible. It means that pipeline stalls are expensive. So a lot of effort's gone into reducing those ones with branch prediction, etc. What's interesting is you can get 4 or even 6 instructions executing at once. So that's different to how you might think. And actually, really, a modern CPU, if you look at the assembler code, that's actually a high-level language. So if you think EAX is a register, it's not. It's actually a variable because it could be any one of a whole pile of pieces of silicon. So we'll come on to that one. So what you see in the assembler code is not what's happening inside the CPU. And if you think, oh, well, that's got more instructions, well, it may be so, but actually, it depends. They may happen in parallel. You don't know, and it's very hard to say. So really, you have to measure. Out-of-order execution. It may not do things in the order you expect. It goes, well, I'm waiting for memory on that one. I've got that one here. I'll start that one because it doesn't depend on that one that I'm waiting the memory, and I'll come back for that one. Okay, so it waits for that. It's doing whatever it can. It's building a dependency graph in hardware at runtime. Okay, that's pretty neat. Branch prediction. This is the problem that you have with pipeline stalls. It's guessing where a jump is going to go. If you say, well, I have all this code here and I have a branch, and executing these bits in the middle in parallel, you've reduced that. So yeah, we're getting lots of instructions here, but we still got that branch. Now that's basically just a jump inside the hardware. It's an if statement inside in hardware. And if you ever put an if statement inside the loop, you'll know that that slows it down. But you've now got one, but it's in hardware. The branch predictors are really very good. The AMD Ryzen chip now uses a neural network for doing branch prediction. I've tried to find out more details about that, but they claim some fancy marketing speak on that. So that's how far they're doing this one, kind of machine learning inside the CPU to do branch prediction. It's that much of an issue. Speculative execution. You can execute multiple things at once and it picks the right answer. Hyperthreading. You can have multiple cores. Because you can say, well, actually, I'm waiting for memory, but I'm going to just do more compute here whilst I'm waiting for that thing to arrive. So it switches between the two. You also have things like vectorization that can go on, and compilers can do vectorization for you, so you can load things faster and compute faster, 128, 256, or even up to 512 bits now. Here's the inside of a Haswell. Nice Intel chip, just to give you an idea of the sort of kind of things that are going on inside here. 56 entry instruction decode queue. So the instructions that come in are decoded into simpler instructions, and it's got 56 of those. That's followed by 192 entry reorder buffer. So it takes those simple instructions, those micro-ops, and reorders them. So if you thought you know what was going on, the answer is you don't. And it's doing whatever it feels like. It's then got this 8-port 60-entry unified reservation station thing. Okay, a reservation station is basically like saying a piece of memory that can hold a register at some point. It's not register 1, register 2, register 3, so EAX or your register can be any one of these things. If you do XOR EAX with EAX, all it does is go and pick one that's already in 0. So it's basically got up to 60 things it can do at once. These can be storing, and we've got things here with shifts. We've got 2 branch detectors. We've got divide. We've got vector logicals. We've got fuse, multiply, accumulates, and 2 things for doing load and store addresses. There's loads of things inside there. The answer is don't try and guess. Do measure, because modern machines are really, really rather important and clever things, much cleverer than I am. And one of the consequences is you can keep jamming that silicon in there, but there's a problem. And the problem is that the memory's out there and the CPU is here. Now, CPU, when it's 14 nanometers, yeah, you can do all lots of stuff like this, but the trouble is if the memory's out there, you've kind of got to go off, down this piece of wire up the other side. So 1 light nanosecond is about this. In a vacuum, it's about that on a circuit board. The trouble is you've got to sort of kind of push electrons into this thing here to try and get this piece of copper to move up and then go down again. Then when you want to go the other way, you have to pull them out. So there's all this pushing and pulling of electrons, which is why it's slow. And what this graph shows you, it's one of many, it doesn't particularly matter, is that the red line is you can add CPU, great. What happens to RAM speed? It hardly has gone up at all. There's a jump at the end here, but this is gigaflops, that's gigabytes per second. We're pretty much limited by memory these days, not by CPU. So trying to save CPU instructions is not the way to get optimization. Make sure that you use the memory correctly is the way to get optimization in most modern things. The consequence of this is 80 or 90% of the time, the CPU is actually waiting for memory. It says on top, or your thing, it measures, yeah, I'm 100% busy. What it's actually doing is just waiting for the memory. And if you've only got 10 or 20% of the time is actually being spent with instructions, if you apply all the compiler flags in the world, you can only add, save a little bit on that. So your 10% might down to 9%, you've saved 1% on your runtime by adding all those extra instructions in, because you're dealing with a memory. The compiler can only deal with a bit, that 10 to 20%. The 80 to 90% of memory, that's your job. In order to make these things go faster, we have these wonderful cache things. And we have lots of those. So modern CPUs have got lots of caches in here. They're nice and fast at doing this vertical kind of stuff here. They're very bad, actually, at doing the horizontal thing. So I'm not going to touch on multi-threading, which is really the horizontal cache thing, because that's really a disaster from a performance point of view. But 1 to 3 cycles, 100 to 3 cycles, you've got a factor of about 100. 2 orders of magnitude between accessing L1 cache and accessing main memory. It could be even worse than that if it's off-board. So this is why using the memory effectively is really important. Here's a lovely picture from Sergei Inachenko. This is time across here, and this is in orders of magnitude. There are 6 orders of magnitude between 10 to the 0 and 10 to the 6 here. Just one thing to point out to you is that concurrency can offer you about 1 order of magnitude. You've got a factor of 100 between here and here. In order to try and make that up with extra CPUs, you need 100 CPUs, minimally, and that's before Amdahl's law comes and gets you. So don't try and throw multiple threads at this to try and solve your problem. Try and solve it by actually using the memory that you've got correctly. So make your single thread go fast before you start adding extra threads in. We've got everything here from less than 1 cycle for simple registered registers, because you're running multiple ones. I'm not going to go through all of this one because there's lots of stuff. We've got branch detection here, 1 or 2 if you get it right, 10 to 20 if you don't. The divide that we talked about here, division, it's kind of slow. Yeah, you don't really want to do too many divisions if you want to go fast. If that's what you need to do, that's what you need to do. They're of the order as the same as a function call. An indirect function call through a pointer or virtual like this with extra parameters in it, 30 to 60. That's about the same as a reading from the L3 cache. So function calls do hurt you. From a performance point of view, so inlining is your friend at this point. More important, main RAM read here, 100, 150, 300, whatever you feel like that. Notice here, allocation and deallocation, 200 to 500 cycles. That's malloc. That's the direct cost of malloc. That's the, I'm going to go over there and going to go and look for some memory. Oh, I found some. Actually, malloc is really a way of saying, please go and find me something that's not in the cache. So nobody's using it, it's not in the cache. As soon as you try using it, bang, what do you get? Oh, you're going to get one of these. You're going to start doing main RAM reads that you've not had before, because it's nice cold memory. So malloc is nice and slow. So let's see if we can get rid of that. Kernel calls, 300 to 500. Context switch, so this would be on the concurrent one. That's 1,000 or so, but that's just going into the kernel and doing the scheduling, coming out again. But the problem with the switch is that as soon as the thread comes around, it goes, right, okay, now what was I doing? Bang, completely cold cache because it's full of somebody else's stuff. So you're then going miss, 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 miss. So you can end up with thousands of cycles, if not tens of thousands of cycles for context switches. So there's just an idea to give you an idea of the range of things that you can have. Measurement. I mentioned it being important. So let's see if we can have measurement on our big O notation. Here's some wonderfully artistically drawn things like this. You may have order n, a straight line. Order n squared, which is really not nice. Order log n, which is sort of kind of flatter, and order 1. Remember, these are asymptotic as n gets very large. And there's a multiplicative factor that's involved in here as well. What you may find is that for small numbers like this, it doesn't matter. Linear search on 10 items is probably faster than binary search, or as fast. You're not going to notice the difference. So do know how big your n is and also check to see how big your K is. You can say, I can do really, really good hashing, but by the way, my hash function takes me about half an hour to calculate. That's not a good use of your time. Also, if you are going to measure, one of the things that I've found, and I have to keep reminding myself, is that the optimizers, at O3 for instance, are really good at getting rid of your code. So you end up benchmarking something that you not think it's doing because you've calculated a result and it's thrown it away. So do that. So do make sure that you don't throw that away. Use the result. It would be nice if we could have everything faster, but we can't. And what you end up doing is making trade-offs, and you make some things faster than others. What's important? And this means knowing your operational profile. This is part of that domain knowledge. What do you want to be fast, and what are you prepared to make slower to make that one faster? Usually 80-20 kind of stuff comes into this one, and classic example, making reads fast and writes slow in a read-dominated system. Tools, plenty of them around. I've mentioned mostly these are Linux ones. There are some equivalent ones around on Windows stuff, and it depends. You can say I have an unmodified application, so I can take the binary as it is and run that one. So I can use perf, older things like oprofile, top. Yes, that's useful just to see roughly what's going on. IO top, I've used that quite often to see what's happening with input and output. The usual VM stat, IO stat, SAR, all those kind of things. Or even just bash and just say, just time this. And it's surprisingly useful. Just if I make a change, does it go faster or not? The advantage, it's full speed. It's often based on sampling. You can usually use large loads with it or something of reasonable size. Commercial ones, Intel have some. You can modify your application. You can say, well, I'm going to put coverage or profiling in there. I can write my own stuff. I can put in the chrono high-resolution clock for sections of code that I'm trying to do that there. Boost has one. You can write your own benchmarking stuff. Google Benchmark allows you to do those ones for micro-benchmarks. You can also use simulators, so the Valgrind set of tools, Valgrind, CacheGrind, etc. They slow it down by a factor of 10, but you get very, very good insight. So an example with CacheGrind is that you can say, all right, okay, I've simulated this one. I can see where the cache misses have come because it actually shows you which line they're on and whether it's an L1 cache miss or an L3 cache miss. So it's well worth looking at those to understand. Data layout and performance. So this is something you'll find in the games industry. They refer to this one as array of struct and structive arrays. And it actually comes up in lots of places. Do you say I basically have my objects like this and I have a vector array of those ones like that? Do I store it in rows or do I store them in columns? Well, it depends. And it may be that you end up actually having to store both for performance. You may have to duplicate your data. And so there are people doing memory analytics who have a row and a column store. If you store it by row, like this, array of structs, and you go through and pull these ones out, then actually you're just jumping around in the memory. You're not using the memory very well. If, on the other hand, I just store it in columns, now I do this, you'll find that is now we're iterating through this in a dense linear fashion. The first one has a thing called read amplification, because it says, oh, I'm going to read this entire row like this. The memory is read as 64 bytes at a time, but actually if I'm only using 4 bytes out of 64 bytes, I'm using 1/16 of the memory bandwidth, actually, for what I'm really using. This is called read amplification. There's a similar thing for write amplification, where I have to read all things, put 1 byte in to write it all back again. You're just throwing away memory bandwidth. That's fine if you only do it occasionally, but if that's what you're doing all the time, you're wasting it. If you go to this one here, now we've got a dense linear pattern like this, the compiler goes, ooh, look, I can vectorize this. So we can use the SSE or AVX instructions. So instead of picking them up, add like this, 4 bytes at a time, 32 bits, it can say, well, actually, look, I can pick up 4, maybe even 8 bytes at a time. So GCC will vectorize like this. Visual Studio does similarly. It's a dense linear access pattern. So if you want performance, a dense linear access pattern is a really good way to go, nice and fast. The generated code for that, well, if I do O2 on this one, you'll see add, so it just pulls out one thing here, moves 4 bytes on and carries on going here. With the vectorization, it's doing it in the XMM and doing 16 bytes at a time. 2.5 times faster on my little laptop here. The hardware may even be prefetching that for you. So it may go faster than you think, not that one, and that's now definitely memory bandwidth limited. Rows at a time, columns at a time. Which do you choose? Well, actually, you may find that there is a compromise between this one. So one of the things you can do is say, well, actually, look, here I had all these fields like this. I had I and F and lots of other things like that. If I'm actually only interested in one or two of these fields, the really common fields, why don't I just store those ones separately? So if I do this, I say, well, actually, look, these are the most common fields, like that. I'll store those separately from these ones. Here I have the hot data and the cold data. And now my hot data is much denser in memory. I haven't got my read amplification problems. So the columns bit, hey, well, that's me. I get to do that. I'm now the developer that I get to do that one, because that's my domain knowledge. The rows, on the other hand, are done for you by the hardware, because it says, oh, look, I can do that in a cache line. So it's keeping things in memory that way. So the hottest of the hot is now you're now concentrating on that, because your cache is full of the hottest things and nothing else. And this is halfway between rows and columns, which is sort of kind of like groups of rows and groups of columns. So you may not have to choose one or the other, but it can be worth splitting this one up to do that. One of the classic techniques, strength reduction. I mentioned if you've got memcopy in there, well, how do we eliminate it? First thing is, do I actually need to make that call? How could I get rid of that call? Well, if I can't get rid of that call, maybe I can reduce the number of times I can do it. Maybe I can cache things. Maybe I can just do bigger things. I can roll them up together as a batch and say, well, actually, why am I allocating one integer at a time? Vector, for instance, puts them all together and says, oh, I'm going to allocate a chunk of these, and now I'm going to allocate twice as many next time. So the overhead of memory allocation of vector is amortized across that one. Loop unrolling is another example of the overhead of the test on the loop. How do you reduce these things? They're classic ones. The old divide to shift thing. Andre likes this one, so strength reduction is one of his big ones. And so I will mention that there. Move semantics. This is C++11 stuff. C++03 couldn't tell the difference between temporaries and non-temporaries. So what you've got there is if you do string 1 plus string 2 plus string 3, you're creating temporaries. You're allocating memory, potentially, depending on the SSO. Things like this, you may be allocating memory and then just changing this temporary and changing this temporary. You've got a lot of stuff going on there. And you couldn't say, well, actually, I want to take this temporary and modify it. You also then couldn't move it. You had to copy the temporary in the end. So that was nice and slow. C++11 introduced move. Auto pointer was something in 03, which was an attempt to do move semantics in a language that didn't allow you to do move semantics. Unique pointer has taken over from that, and that does actually do move semantics. Yay! And we've added our value references, move constructors, move operations, just for a basic kind of introduction to this one. On the left here, what we'd have to do before with this one, where this is a buffer here with so this is an X with a pointer to an allocated buffer. If I wanted to move this one, I couldn't. I have to make a copy, which means allocate, copy all the bytes across, move the pointer, and then delete the original. So you end up with an allocate and a copy and a deallocate. This is a real waste. Whereas in the move world, you say, take that one, just move the pointer. Yay, no allocations. You've just got essentially a couple of assignments to do it. So where does it happen? Well, in all of these ones here, if I'm returning by value, all of these ones here are then going to be copies in C++11. This one here is returning a temporary, therefore that's a move. It calls the move constructor. This is an L value, so LHS here has got a name and therefore it's treated as an R value. It won't move from this one, but you can be explicit and say, please move from it. Here be dragons if you're not careful, because you've moved from it. You now have an object which is in a state that you're not quite sure what it is. It's a move from state. Move semantics very useful. How do you implement them? Well, Notice that, so these are, in this case, what I've got here is just pointer assignments. So I just move the copy the pointer across and null that one out. The move assignment has to clear the left-hand side first. Notice I've also done no except. No except here is important for libraries, for things like making sure that your vector can move things, not actually having to copy them. Which leads us also on to the subject of resource management. So very briefly, you may well have come across the rule of 3, which says, okay, if I have any of the copy constructor, the copy assignment, or the destructor in my class, I need all 3 in order to make it work correctly. In C++11, we added in move constructor, move assignment. This became the rule of 5. This became really boring. And it's meant that you had to do a lot of stuff. And actually now, the rule of 0 is the way to go. And also from a performance point of view, which is do not do any resource management in your classes. Use the standard library. Use things that copy and move correctly, and then you don't have to. It saves you a lot of time. It saves you a lot of heartache. It also can mean that you end up having faster code. An interesting thing, a discussion I was just having earlier, is that if you have a class with a unique pointer inside it, just a unique pointer, it then becomes move only, which means that you can't go around and just accidentally copying it and copying data. You only got a pointer to a megabyte of data. You don't want to copy that accidentally. It's now move only. You can now have to make an explicit copy, so you've stopped the accidental copying. A quick example here of taking 10 million integers and putting them to a container, essentially doing pushback or insert into them in sorted order. Vector without any form of optimization does 25 allocations because that's a 64 megabytes plus then the 32 that was before, plus the 4, but all the way down to here. So that's the 25 allocations. Dec, 78,000, because they're 512 byte pages. But if you notice, these other ones list unordered set and set it at 10 million or so. The reason unordered set is higher than that one because it's got buckets and other things to allocate. If they're thousands of cycles, guess what the performance of those is going to be? You're not going to do very well with these ones if you do a lot of allocation like this. So be careful with the STL and how you might use that. We can optimize it. Vector, instead of the 25 allocations, I can reserve it. And that now says, right, okay, I can reserve 10 million, and I get 1 allocation. And notice I get that improvement here. And it just has exactly the right amount of memory. Rather than 64 megs, it's 40 megs. So reserve, one well-known way to use vector. It's also safe. It's safer than just saying it's an array of this size, because if you now push an extra element, it will still work. It just has to go and reallocate. It just saves you the time getting there. A set, if you're going to put things in here, the domain knowledge I've got here is, I'm putting these in sorted order. So if I just insert them, it'll start at the top. It's a balanced binary tree. So it will have to go and find this one here. And there's 10 million of those. Then we've got log to base 2, which is, 23, 24, something around that, things, of how many comparisons I've got to do to get there for the last ones. Number of allocations, etc. Well, I could say, well, why don't I start somewhere else? You can provide a hint. I can give it exactly the wrong hint and say, why don't you start at the beginning? And essentially, I'm saying, you know that 10 million, why don't you start at 0 down here and see where you go? And then it has to go all the way through the tree, which is why it's slower. If, on the other hand, you say insert at the end, wow, here we go, much improved because it's now just at that one end. You've cut down all that search to the 24 to go. So watch out for things like hints. Just a few things about standard containers. That's for the writes. Remember that this was also about trying to reduce the number of allocations, because we know that allocations will often dominate. Finding items. Lots of stuff in data structures. Here's a random lookup into some of these ones here. What happens if I use standard find? What happens if I use the STL incorrectly? And what happens if I use the containers correctly? So I've got a bunch of things like this. I'm pulling out some random values and number out of that. So I've got 10 million, I'm going to do 100 finds, generate 100 random values. Haven't done a pushback. Here's my timing loop. Standard find. This is the Don't tell the optimizer not to eliminate this one here, because otherwise it just throws away the results of that. That's what that's for. The linear find works well on vector and dec. List is relatively poor performer, and for exactly the same reasons that Phil Nash mentioned. This is like pointer chasing. It also doesn't use the memory bandwidth very well because we've got 24 bytes per element rather than 4 bytes per element, so it's memory bandwidth limited. Unordered set is actually quite good on this one because it's actually internally it's a singly linked list. Set is not particularly good at all because it's got more pointers to traverse. So that's a linear search, but we know really that unordered set and set, you shouldn't be doing that. Really, please don't do that. So let's have a lot more of these ones here for 1 million lookups, and let's actually use the container one, and now we're in the right sort of kind of place. 10,000 times faster, excellent, yes, that's what we want in the first place. Domain knowledge comes up in a moment, which we'll deal with vector in a moment. Hashing. Hashing can be a lot of fun. There's some optimization about the hash function. And hashing functions, you need to know about how well they're distributed, how well that they split things up. Well, the GCC library says if you give me an int, it knows, I don't need to hash an int, I'll just use the int. So actually it does no hashing at all on int. And if I try to provide an int hasher myself that basically does the same thing, it gives that result. If I say a float instead, it goes, I don't know about that. So if I use float, you can see it's notably slower, but if I go back to a float with a hash function that's just the conversion of that one, we're back in the same thing. So watch out for your hash function. If you're doing a lot of these things, you can end up with a slower lookup table than you wanted. That hash, by the way, is an FNV1A hash that just takes the bytes one at a time and does an exclusive OR and a multiply. I mentioned how do we get faster on these things? Well, vector and dec. We know domain knowledge tells us we put these in orders. Now got a sorted vector. Maybe we can do binary lookup. So binary search or lower bound. Binary search just gives you back true or false. Lower bound just gives you back an iterator. And notice that vector is actually faster than set for that particular one. It's dense in memory. Dec is not quite as fast because they're pages of memory. You have to go through a vector of pointers to find it. So again, this is just the use of domain knowledge. Which leads me on to this. There's a lot you probably know that you can't put directly into your code. And this is what really will make the biggest difference. So what are the relative probability of these operations? How many reads, how many writes, what do you do? That's the thing you need to understand in order to say, well, these are things that need to go quickly. Don't try and make everything the same. I had one client that was trying to make everything look the same. And this was in telephony, and they were trying to save everything, so they were trying to do a complete failover and duplication of everything else. And I went, well, guys, there's a reason that you can't go this fast. It's because you're trying to do the same level of safety on something here that just says you've used an extra kilobyte of data on your mobile plan as to that 911 emergency call over there. That's really not the way to go fast. What's the worst thing that could happen if you lose this? Well, somebody gets an extra kilobyte. Actually, it's not worth trying to save that too much. 911, you stop the entire world to get that emergency call through. So don't treat everything the same. What's good enough? That's also something that people seem to forget, that faster is better. Well, actually shaving 1 millisecond off the startup time of your program by optimizing your configuration reading to do things in the right way with string views because you've saved a few allocations, well, probably not necessary. What do you know about the data, the size, how long it is? How long are your keys? Are you going to be using strings that fit into SSO? Are they all variable length, or are they all the same size? If you're using product codes that are all 6 or 8 long, or your ISBNs, you know what size they are. Why are you using dynamic data structures when you know how big they are? What's the distribution of your data? What are you doing? You're doing batch or OLTP. These are the things that will give you more gains than just trying to use the STL or compiler flags. I've got 6 questions that I'm going to go through just to say, well, okay, These are things which are very important to understand from a performance point of view about the data, the way you use it. Primary key lookup, non-primary key lookup, range scans, read-write, working set, and consistency. So, primary key access, most common form of access. Database primary key, that's a classic example. So, unordered map or map, classic example. I'm just looking that thing up. I'm looking up a financial instrument by a number. I'm looking up a customer. Lots of things like that. You can use hashing, so that's order one. You can use binary search or linear search. You really only need an operator equals equals to do this. There's no ordering, you don't need anything else. You can just say it's that one or it's not that one. It's very straightforward. It allows you to partition things. If you come to a conference like this, you may say, well, actually, okay, people with surnames A to L go into this queue, people with M to Z go here. Perfect partitioning, fantastic. The two don't need to talk. You get almost perfect scalability. So primary key lookup, absolutely wonderful, great. Product catalog, you're typically looking at products by individual numbers there. Customer records, I want that customer. Web sessions, you don't want to go and see anybody else's web sessions, you're not iterating across them all. No SQL kind of key value stores. Memcache, for instance, doesn't even have a way of iterating across keys. You can only look something up, you can't find out all the keys or iterate through them. That's the most common one. Non-primary key access. So what do you need in terms of looking things up not by the primary key? Show me all accounts with a balance greater than 100. So often looking at by value, not by the key. In a database, this is a secondary index. If you're building these in memory, you may need some additional maps that point into other places like this. Maybe you're looking at parts of a record. Do you need to search on metadata? So are you looking up, oh, when did this happen? Who did this? In certain cases, you may actually need full text search inside. It's substantially more work. So on the web, for instance, primary key access is a URL. This URL, don't care about anything else, that's really fast. Non-primary key access is called Google. It's a very, very different kind of thing. So you need to understand whether you have this, whether you need this or not. So it's almost always slower. Range scans, sequential access. Phil was talking about looking things up, and he had his hash maps and ordering. So a binary map, binary tree, you're paying for the cost of knowing they come in a particular order. With a hash table, you go, I don't care what order they are. And you actually gain a significant amount. This is why an unordered map may well be a lot faster than an ordered map. Don't use a map if you don't need the ordering, because you're paying a price for it. This requires operator less than. You're probably going to need iterators. You may need some sort of kind of traversal state. There's a lot of things going on in this area. You may need to do a seek followed by a scan. Hadoop is really good at this one. You go, oh, go and find that thing here. It's 5 milliseconds to find the block. Then I got 64 megabytes of data coming out. That's a very nice, dense linear fashion. Watch out for things like the N+1 database problem. If you're doing OO-based programming or using an ORM, it's very easy to say, oh, I want that one, I want this one, I want that one, I want this one. You go backwards and forwards to your database, and you can call 1,000 records. Each is maybe 3 milliseconds. That's 3 seconds to do those ones. Whereas actually one SQL bulk call might have done the whole thing in maybe 20, 30 milliseconds. So watch out for bulk and see when you want to use that, particularly in things like distributed systems. It makes quite a difference on your read-to-write ratios. If you've got a lot of read, caching is your friend. But you then have, say, well, okay, this is application caches as well as memory caches in the hardware. What do you do about write-back? What do you do about eviction? How do you keep those up to date? What do I need about here? You may well find that actually the metadata is worth caching, but the data itself is not worth caching. The index structures are very useful. In certain cases, you're doing data logging, and caching really doesn't help you much, other than the metadata, because you're just writing and writing and writing on the end. So knowing this read-write ratio is a very important thing for performance point of view. Working set. How much data have you got? How big is it? So these are pictures at the bottom here. If you have something like a news website that's People are coming in here and they're starting to look at today's articles or yesterday's articles. It's very strongly biased towards a small set. If, on the other hand, you go to the airport like this, most people travel once or twice a year, you will probably find that actually you've got a very flat kind of approach here. And there are a few frequent flyers and crew up the top, but the rest of it is very flat. And you're dominated by I/O here, in the passport case, and the news case, you can fit it all in RAM. You get a very different answer. I was speaking to somebody yesterday. He said, well, actually, he was dealing with publishing, but it's scientific publishing, and it's all long tail. The documents are all 40 or 50 megabytes of XML, and there is no peak out here. It's all like that. He's basically got that, even though it's the same publishing thing, just because of the access ones. So this is then how much will fit. Do I need a bigger machine? Can I actually fit this one here? Is it worth trying to do compression on my data to try and fit it in because that saves me the overhead going to the disk? All of these things are very important to understand from an optimization point of view. The last one is consistency. Acid versus base transactions. If you're doing airline booking, there's like one seat there on that aircraft. You need to know whether you've got it or not. And that's a very different matter from saying, yeah, I've got a hotel here, and I'll just say, has the hotel got Wi-Fi or not? Doesn't really matter if that happens now or a little bit later. You need to understand that one, because if it's ACID and it's transactional, you're probably going to have it centralized, and you have locking, two-phase commits, all those kind of things, which is a very different matter, because you won't be able to speed that up anywhere near as much as you'd be able to speed up the base kind of stuff with copies and other things. So understanding that is very different. And again, it may be data versus metadata. So your transactional data may well end up being ACID, whereas your reference data is not. So that's an idea of kind of that middle section there. Once you've got rid of your memcopy and some ideas about memory structures and other things. Down there, we may also be looking at strings. Strings, as mentioned just before, reference counted in the 98 standard, or specifically allowed to be. The C++11 standard specifically said it was not allowed because you don't want hidden shared state inside the STL because of the memory model and the concurrency issues. GCC moved to that in version 5. Visual Studio has been using the SSO non-shared version since about Visual Studio 2005. We've got the lovely string view coming up. Boost string ref similarly. You could use arrays of chars or even C-style char pointers. And we end up with some choices. And again, I can't really tell you which is the right one. Domain knowledge is the thing that's going to do this one. If you have char star, well, it's variable size, and you don't know about the memory allocation. Maybe it's all statically allocated. I don't know. You have all the functionality. It's external things like strlength and strcopy, all those other things. And there'll be a null at the end, which is good. But you have all this ownership problem. You don't know if you're pointing at something, whether it's owned or not. Is it going to go away or not? And obviously, there have been all the problems over the years with buffer overflow because it forgets its length. It's one of the reasons I really, really don't like using char stars. With arrays, so standard array of char n, fixed size, there's no malloc, you know what you're getting there. You get most of the stuff from an STL container, including an operator less than, by the way, but it's a byte at the time. So this is where you'll get, this will translate to memcomp. Up to you whether you have a null on the end or not. If it's fixed size, you may not need it. You have ownership, nice and cache friendly, because it's, I want one of those, it's right there. It's not dynamically allocated, it's right on your stack, and the stack is almost always hot because you're not suddenly looking off into the heap. But there's no move operations because it's fully owned, because there's no pointer to do, so move is the same as copy. Version 4 string and version 5 string have slightly different characteristics in terms of the size. Notice with the GCC one, for instance, it's 32 bytes. The Microsoft one is 24 bytes, if I remember rightly, because it's 3 pointers. They haven't got this 4th pointer in there. Lots of functionality, lots of nulls, etc. You don't have to worry about ownership, and you get the SSO kind of stuff. String view, 16 bytes on a 64-bit machine, because it's pointer and length. No malloc, it's great. It's basically constant string. You don't have a null at the end. because it's pointer and length, but that's again part of its big advantage. You have got this ownership now. You've said, right, okay, I have to know where I'm pointing. You have to know where it's still there. And so that is a proof that you now have to take on. It's basically a fat pointer. And the advice these days seems to be passing by value. So just to go through some of those ones again, we start off at the top. It's too slow, you start profiling, you get the silly kind of, oh, why am I doing that one? Moments. Often this is about a strength reduction. How do I get rid of some of those ones here? Then I usually find that you're into sort of kind of malloc and memory allocation issues and memory copy and memcomp. Memory comparison, for instance, if you're doing lots of stuff with maps, because it's going to have to go through a big map and do all that memory comparison all the time. This is where having temporaries can hurt you. So this is where, just to go back over, this is where move can help you, or pre-allocation of your memory, or saying reserve on my vector, because malloc is not cache friendly at all. And also we'll have pointers in there, which is again taking away off your stack. This point, I would then start looking at my the choice of my STL containers, or other ways of doing it with, say, open addressing hash tables. And at that point, I can start doing the thing of saying, well, actually hot and cold comms and separating those ones out. So that leads us into sort of kind of the last few things about this one. The strength reduction. Things like static. If you're creating an object in a function, how often do you create it? You're creating every time you call that function. Is that constructor causing you too much trouble? For instance, if it's a vector, I allocate it and I deallocate it. Allocate and deallocate. Maybe you should use a static, allocate it once, and call clear at the end, or clear at the beginning, to hold on to the memory, but basically get rid of the contents. Silly things I've seen. People doing log all these arguments. Well, it's all right. We haven't got logging turned on at the moment. Only on that's a debug, and we've got it set to error level. It says, yeah, but you're actually calculating all those arguments, transferring them, sending through to the log thing that has an if statement inside that throws them all away. So basically, you're throwing all that performance away, creating all these objects and doing nothing with them. And so the advice there was for your log macro to have if log level equals is greater than debug, or is less than debug, do this. So don't calculate all the arguments. It's just a few things I've seen. You can do things like string interning. If you've got lots of strings, back to the immutable strings, you go, I know what the strings are on this one. I got an example which is looking up 5,744 airports. We know what the IATA codes are. If I got all those, why am I storing these all? Do I need multiple copies of these ones? Do I need multiple copies of the name? London has several airports. Do I need London several times? Maybe I can actually put all those into one to reduce the size of my memory, and then use a string reference, use an index into a series of strings. And if I have that, well, if I've got my statistics, I can now put all the common strings at the beginning and the less common strings at the end. That's making me more cache friendly. Instead of having an 8-byte pointer, I can now have a 2 or maybe even a 3-byte index into this one, and I've then made my cache smaller. Don't use ACID when base will do, because that limits a load of stuff about you getting into locking and all the other things that you're doing that one. So there's overheads to doing to do ACID stuff. I've seen people doing stuff and they're calculating the time all the time and changing the time into a string. And a friend of mine who does tuning on IBM mainframe stuff, he said he found that actually in one particular case, the top line there was converting times into strings. So be careful of that one. If you might as well just do it once per second, if that granularity is good enough, do it once, and then you go, I'm going to use that for all of the 100 things I'm logging after this. Devirtualization. You can devirtualize your calls. If you, by use the keyword final, for instance. If you have, in C++11, you have virtual calls and you have a final, you have a pointer to that one. If you say final, then the compiler knows that there cannot be anything below that, so it doesn't have to do the virtual, so therefore can inline the call. And that then says inline here, inline in there. So final on the edges, it's safe, because if you try to inherit from it, it won't let you. and you'll find out the compile time. So use of final can help you there. Fast path and slow path. If you know what the fast path is, detect that very quickly and cheaply. You can say, right, this is one of my 80% ones. I'm going to do that one here. If it's going to be, and I want to have something that doesn't have any false negatives. If it pushes me into the slow path, occasionally when it shouldn't do, that's fine. But I want to be able to say is, right, in the fast path, there's no memory allocation, there's no locks, there's nothing. It's like straight in there, straight back out again. So again, that's knowing your 80-20. You can save yourself tens of thousands of cycles with this one. Avoiding mallocs and copies. So strings, how do you use those? Avoid temporary strings, string 1 plus string 2 plus string 3. Maybe you use plus equals. Maybe you can use string view instead. Watch out for conversions. It's actually surprisingly slow to convert integers to floating points and the other way around at a low level. Use move. A number of people you'll now see using sync arguments on constructors. You'll pass by value and then do a move inside. That is counterintuitively faster on a number of compilers these days. Pre-allocate your memory. Use return value optimization. So returning by value, you'll find that actually the compiler doesn't even do that one in C++ 17. It's mandated that that optimization happens. So use the rule of 0, preferably. If you use inheritance, avoid deep inheritance hierarchies because you've got a lot of constructors to call. That's much less of a problem than it used to be. String view, as I said, avoids allocations. Watch out on algorithms. You may find that you can, order n, log n, 1, going vector map, unordered map, or your own hash tables, very useful. You'll need to know about your data access patterns and whether you require ordering or not, and how you want to handle those strings. In terms of cache effects, array of struct of arrays, maybe you can do hot-cold separation to say, these are the pieces of data I want most, and then crunch them up that way, and then let the hardware do that one. You have a choice of hold by pointer or hold by value. Holding by pointer is this form of hot-cold separation. It allows you move semantics, but then you get this trade-off with it being through a pointer. So you have to do some measurements to understand that one. A lot of these ones here, these cache effects, also depend upon the size of your data, because you've got 32 kilobytes of data cache and those other things like that. Watch out for read and write amplification. If you're going to read something, make sure that you're using everything that's inside that. Don't read data you're not going to use. Playing around with the compiler optimizations is fun. The vectorization is particularly fun. And inlining. Inlining is definitely your friend on this one. So, multi-level problem. It's not just a set of tweaks. So I'm trying to provide a way of the order which you might want to look at those ones here, and stressing that domain knowledge is really a key to this one here. Donald Nuthon knew that a long time ago, and we seem to have forgotten it. Or actually, if we do, we just don't make it explicit that we know that we're using it. And that will beat your clever algorithms all the time. Go and find some tools, learn how to use them, learn how to interpret them. That is it. Any questions?